Alright, y'all, we're back. Here we go. Let's talk about... Why does that look weird? Whatever, it's okay. Okay, so we're talking about section 5.1. We're talking about area. So everything we've done in this class so far has been about how things are changing. So with limits, we were looking at how functions were changing, as like how the function value was changing as x, as our input to the function was going towards some number. It could be a finite number, or it could be an infinite number. As we're looking at the derivative, that's how the function's changing in terms of its slope. So, and then we were looking at all the different applications for how we could use the rate of change of our function and the rate of change of the rate of change for our function, which is looking at if the function's concave up or down. So those were all things where we're looking at how the function is changing. The rate of change of the function is changing. The rate of change of the rate of change of the function is changing. So now we're going to backtrack a little bit, and we're going to look at how area works. Because, I don't know if you remember, but in the very beginning of the class, we read this reading about how there's derivatives, and there's, so the derivative is looking at your slope, and then your antiderivative is looking in the opposite direction, so you're getting like an inverse relationship. So that is coming soon. Don't fret. It's coming. But for now, we're going to talk about area. So we're going to hit a little bit of sigma notation, which might be familiar to you, might not be. It's totally fine. But it's just repeated addition, and it's a different way of looking at functions. And sigma notation is going to come up in unit, I think it's 9. I lose track of the numbering, but it's in the second semester. We're going to talk about summation notation and how that is combined with functions so that you get a different way of thinking about how functions can happen. And if you're a computer scientist, then this is very exciting to you because it's thinking about indexes and all that. So that's nice. And then we're going to talk about some rules with our sigma notation, this operation of summation. And then we're going to talk about a couple of different ways of approximating the area under curves. Because we can, once we have an approximation, similar to our secant line, how we were figuring out with the secant line, the approximation of what a slope is, with area under curves, we can approximate that, not using a secant line, but actually using rectangles. So, let's get started. We have sigma notation. So this is a capital Greek letter sigma. Little sigma is, oh, that's a bad place to put that. But that's a little sigma, and this is a big sigma. Sigma is spelled S-I-G-M-A in, I guess, English. But sigma starts with a S, so the S sound gives you sigma, and it's lovely. Repeated sigma, repeated addition is summing or summation, and so that starts with S, sigma. And then for repeated multiplication, that's repeating the product, so that is capital pi. Not to be confused with lowercase pi, which looks very similar. But there's actually there's a statue at UMCP, UMD, College Park, which is a capital pi, and it's very cool. So if you're ever on campus, or if you're on the Google Street and you want to look at College Park's campus, they have a capital pi. If you grab a screenshot of that, then I will be very pleased with you if you put that in your math journal. So, sigma notation. Focus, Mrs. Contreras, concentrate. The sum of n terms, a1, a2, a3, ... to an, or a sub n, that's another way of saying that, a sub 1, a sub 2, a sub 3, a sub n, is written as sigma, with the little I down below, which is the index of summation, and so it's going from I equals 1 to I equals n, which is the number of our terms that we're looking at. A sub I is the ith term. So a sub I is the ith term of our sum, and our upper bound for our summation is n, and our lower bound for our summation is 1. So we're going from 1 to n in our counter for our terms, which are denoted with these little subscripts. So when we're reading this, I'm going to erase this so it looks a little cleaner. We're saying this is the sum from 1 to n of a sub I. And that's going to be a sum of all of the terms going from 1 to n. Okay, so we're just looking at addition. That's what we're doing. We're looking at repeated addition of some rule that we're given, and we're going to add that repeatedly until we stop. So we have a starting point and we have a stopping point. So if we're adding up, so there's some rules that we have, which I hope intuitively do make some kind of sense, because these all depend on those properties that you learned in like algebra. So if we're looking at, let me zoom in a little bit, if we're looking at our function, or if we're looking at, our terms that are in terms of a's and also b's, and we also have c is a constant, then the things that we have here, they're going to hold. So when we have the sum from 1 to n of some constant c, that means that we get n times c, because each term is going to be a c. We're adding just c, and nothing is changing because there's no i's in there. There's no i's. See, there's no i's. No, there's no i's. There's no I element in what we're doing, so we're just adding up a certain number of c's. And how many c's are we adding? N c's. So that it's just the repeated addition is the definition of multiplication, which is a throwback to what, like 3rd grade or something, so that's fun. So, what else do we have here? We have that when we have a constant multiplied by our a term, our ith term, when we have our constant multiplied by our ith term, then we can actually factor out that constant and just deal with the ith term by itself, because this is like c times a1 plus c times a2 plus c times a3 plus dot 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 plus c times a n. And so because of factoring, we can factor out c and then just have a1 plus a2 plus a3 plus dot 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 plus a n. And that's lovely, because that's just our constant term, our scalar multiple, times the sum that we have right there. So when we have a constant times something our ith term, then we can just factor it out. Addition works the way that we think it works. If you're adding up two different terms, this is going to be what, a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus dot 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 plus an plus bn, and then we can just group them. So we can use the commutative property of, oh, that's a bad circle. We can use the commutative property of addition and shuffle these around so that we have all the a's in the beginning, like that, and then we have all the b's in the end, and then we have that our sum of our ith terms, a sub I plus b sub I, that equals our sum from i's 1 to n of a sub I plus our sum from i's 1 to n of b sub I. So the rearranging happens because we are using the commutative, can I spell commutative? Property of addition. Addition. Isn't that lovely? I think that's quite lovely. And the next one we actually have is a combination, effectively, of 2 and 3. So here, this was factoring out the constant, right? So, did we not just factor out a constant with the constant being -1? addition and subtraction are the same. Like, subtraction isn't really a thing. It's just adding with a negative. Don't tell your third grade teacher that, though. So, we have a sub I minus b sub I, which we can rewrite as a sub I plus negative b sub I, right? Like, that's something that we can do because of multiplication. And then, don't we have rule 3, where we're looking at this is equal to the sum of a sub I plus the sum of negative b sub I from I equals 1 to n down there, and we're responsible. I'm actually like really bad at keeping track of these, so please do help me keep track of them. I guess you can't yell at me through the screen, but just like, remind me in class would be helpful. And then this is using rule 2, where we can factor that out, so that's equal to the sum from I is 1 to n of a sub I minus the sum from I is 1 to n of b sub I. And we can break up our sum into 2 different parts, or as many different parts as you want to, as long as there's enough indexes to deal with. But if you're looking at like the sum of a sub 1 plus a sub 2 plus a sub 3 plus ... plus a sub m plus a sub m plus 1 plus ... and we're making sure that m is like less than n, right? Like that's something that we assumed up at top. So we have a sub n. So our sum, we can look at separately. We can have the first part of the sum plus the second part of the sum, and our indexes just need to match. So we have, this is going from 1 to m, and then this is going from m plus 1 to n, right there. Probably should have changed colors. It's okay. Alright, so those are some rules. Scalar multiplication works the way we think it will, addition works the way that we think it will, and subtraction also works the way that we think it will. And we can break it up. Also, when there's no i's, then you're just multiplying. Cool. So, let's try some of these. These seem like good practice problems. Try A. What is that going to be equal to? So we're just adding up the numbers from 1 to 6. What about B? What is B going to be equal to? Now our index is starting at 0, so be careful about that. B is going to be the exact same thing. Wild. Don't these look like little hungry caterpillars to you? The Eric Carle book. Very hungry caterpillar. It's like, you just need some like little ears. Not ears. Antenna. Okay. What about when we're looking at our index of summation from j equals 3 to j equals 7 of j squared? What's that going to be? We're just going to add up 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Alright. How about for D? We have our index is k. Our index of summation is k. We're going from 1 to n, and we have 1 over n times k squared plus 1. So it might look kind of similar to C, but there might be something different, right? Because we have this dividing by n business, which I wonder if that will be useful later. Probably. So we can just tag that 1 over n along, because since it doesn't have any k's in it, we effectively treat it as a constant, but you can also factor it out, right? Because 1 over n is a term, is a factor in each of these terms. So we can factor out a 1 over n if we're feeling lazy. I probably would if I were writing it out. Alright? And look at E. Just like soak that in. What does that mean? And what does it look like? Remember, we've talked about slope a lot. And slope looks division, or yeah, division of like change in y over change in x. So here we have y times the change in x, which looks vaguely like that linearization thing that we were doing, kind of, but not quite, because it's not a derivative. I wonder if you're going to get the area of a rectangle, right? An area of a rectangle with base delta x and a height of f of x sub I. Interesting, interesting. So, what we end up with is evaluating our function at various locations and multiplying by some change in our x direction. So change in our x direction, and then we have some height from our f sub x of x sub n. So we have that height times that base, and we get an area. I wonder if that will be useful later on. Yes, it will. Okay, let me see. So these are, I guess, nice to know, but not necessarily things that need to be locked into your brain at this moment. But there's a story about this one with, there's like, I think it was Gauss. He was kind of a dunce in his school. He was like, he was kind of like a jerk to his teacher, because he was really smart, and, I think it was Gauss. Maybe it was Galois. I don't know. It was one of those guys with like, I don't know. It was someone in math history. But they were like really obnoxious when they were in elementary school. And so then their teacher was like, hey, I'm going to draw a really big wig for the teacher. Hey, kid who is obnoxious in my class, you need to go and you need to count, or you need to add up all the numbers from 1 to 100. And go sit on that stool for dunces until you've done that. And so the kid, and I really forget who it was, thought about it for a while, like maybe a couple minutes, and then was like, hey teacher, I figured it out. And the teacher was like, how did you do that? And it's because of this formula. So, and you can definitely math journal about, who that actually was, because I don't remember. Yeah. Okay, but, when you're adding up all the numbers from 1 to something, you just take the biggest number, and then you add another number to it and divide by 2. Because you're pairing up the numbers. So, that's nice. Okay. And then when you're looking at sums of squares, of consecutive integers that are squared, then you get this lovely formula, that might be useful when you're doing stuff like, well, summing squares is very important for trying to find like least squares of things, and then cubes, this is another just way, it's like a higher order of looking at things. It's nice. Okay. So, what were we originally talking about? We were originally trying to talk about area. The goal for today was talking about area. So the goal for today was talking about area. The blue part, that's the area under the curve, right? And it's bounded by this function f of x and the x-axis, and we're going from some x value a to some x value b. So that's what this picture is showing us. So how can we figure that out, though? Seems very difficult. Because, like, how are you going to make this curvy part? Seems like too much. So, how are we going to try to get started? Well, we need to define some stuff. So, if we're going to have a set of points, and the points are determined by x values, the points that we have are going to be, they're going to make something called a partition. The set of points is going to become a partition if we're looking at an ordered set that's going from A, so our endpoint A, to our other endpoint B, and we're going to form sub-intervals. So we're going to take this interval from A to B, and we're going to slice it into how many slices. There's going to be n slices happening, and we're looking at like a x sub 0 to x sub 1, and then from an x sub 1 to x sub 2, and we're going to keep on going from there until we've covered our entire interval. We also have a fancier name for that, is called a partition, and if we have the subintervals are all equal sizes, which is nice for some things, not necessary for other things, but if we have the same width for each of our little slices, our little partitions, then we're going to call that a regular partition. Just like regular polygons have all the same side lengths and like all the same interior angles, regular partitions are when all the intervals are the same size. That's nice. Partition. So what are we going to use a partition for? Well, if we're looking at, remember how we talked about area, how this, where'd it go? Yeah. Where this was going to give us an area, and it's giving us an area of a rectangle that we're evaluating at some function, and we're multiplying by some change in x. So this, if we're looking at this is a regular partition with a constant delta x, so that's nice. And look at this. So we have a left endpoint approximation, or a left rectangular, left Riemann sum, and this is going to be a regular partition for this, where we're looking at the area of our rectangle is denoted by evaluating our function somewhere on the left side. So how are we making sure that it's on the left side? We're looking at our I minus 1. So we're looking on the left side. I'm not mirrored, and it's like really confusing. So this is actually my right hand, but we're looking from the left side of the function to the right side of the function. We're trying to evaluate at the left side. And how do we do that? Well, we need to look at the x sub I minus 1 to look on the left. So we're calling this number A the left endpoint approximation using our subintervals. And how many subintervals are we looking at? We're looking at n subintervals. So we're taking our whole interval and we're slicing it into n pieces. And on each of the n pieces, we're evaluating our function at the left endpoint of our interval. And then we're taking that output, that f of x value, and we're multiplying it by the size of our interval. So our size of our interval is how the x value is changing. And so when we write this out and we don't feel like doing all of that writing, we can write that with our summation notation. Now visually, what does that look like? We're looking at our left endpoints on our interval using this partition of n slices. And it's a regular partition because each of these intervals is the same size. Each of these subintervals is the same size. So clearly you can see that the area of the rectangles that we have here don't fit exactly with what the area under this curve is going to be, which is disappointing, but there are some ways that we can mitigate that error or that discrepancy in what the area is. So, yeah, that's the left endpoint approximation. So we also call that the left sum. So if you're looking at a left sum, then of course we're also going to need to talk about a right sum. So if we're only evaluating at the left endpoints for our left sum, then what do you think we're going to do for our right sum? We're going to evaluate at the right endpoints. So right endpoint approximation, we're constructing our same rectangle, we're looking at our subintervals, but now we're evaluating at f of x sub I. Instead of x sub I minus 1, we're looking at x sub I, and that's where we're evaluating our function. we're looking at the areas of rectangles, so we're taking that height of our function and we're multiplying it by the change in our x value, and we're doing that repeatedly, so you're getting, again, lovely sigma notation, where we're evaluating our function at x sub I, not x sub I minus 1. That was for the left sum. And we're multiplying by our change in our x value, which is the size of our subinterval in our regular partition. And we call this the right sum, because we're looking at the right endpoint. And what's a picture of that look like? Oh, well, this is the same function that we were looking at before. But here, we are evaluating at the right endpoints. So do you see that now we have actually an area that's an over approximation? It's too big. It covers over what the actual area is. So think about some ways that you would, at this point, get armed with your right sum, or with your left sum, and with your right sum. What would you do to try to get an even better approximation of what the area under the curve will be? And here's another side by side. If we're looking at 6 partitions, then we're indexing starting at 0. We're going up to 6. And how many rectangles are we making? 1, 2, 3, 4, 5, 6. And how many rectangles are we making here? I think it's 6. 1, 2, 3, 4, 5, 6. Yep. And our change in our x value is the size of our base of our rectangle. And that is also the size of our subintervals. And the height is evaluating for the left sum at the left endpoint on that subinterval. And our right sum is evaluating at the right endpoint of our subinterval. So, what you need to do, try it now. Sketch the left endpoint and right endpoint approximations for f of x equals 1 over x. So that's a one of those. What is that? Is it this way? I think it is. On the interval from 1 to 2, and use n equals 4, so you're getting 4 rectangles. You're going to approximate your area using both methods. So try that out. Okay, so I did this in Desmos, but you did it by hand, hopefully, maybe. So we're sketching, and then we're finding our left endpoint and right endpoint. So in order to get 4 pieces, we need 5 different points. If we're looking at our left endpoint, then we're getting, I should scroll up. So we're looking at this rectangle plus this one plus this one and plus this one. So the delta x is looking at 2 minus 1, right? Because this is starting at 2. Or we're going from 1 to 2, so 2 minus 1 divided by how many subintervals are we looking at? We're looking at 4. So 2 minus 1 over 4 is 1 over 4, which is 0.25, which is what's showing up more here. So we're multiplying by 0.25 times the sum of what are the heights? We're looking at 1 plus 0.8 plus 0.6 repeated plus this, which is like 7 over 4, right? So 4/7 plus, what is that? 1/2. So that's our left sum. And then our right sum is going to be our partition size, and I should change colors. So our right sum is going to be 0.25 times the heights from the right endpoints, which are almost all the same. The only one that's different was this end and this end. So we got that is what, 0.25 times 0.8 plus 0.6 plus 4/7 plus 1/2. Oh wait, hold up. Did I do that wrong? I did. 1, 2, 3, yeah, it's not a 1/2 there. This is a 4/7, and that's it for the red one, and then that's the 1/2. Okay, so yeah, those are your numbers. Which one's bigger? The left sum, right? Left sum is bigger. I wonder if there's like generalizable things for left sum being an over approximation versus right sum being an over approximation, when that would be. Sorry if there's like random banging happening. One of my neighbors is moving, and so there's movers happening. The stairs are right there. Sorry. Riemann sum is named for some Georg Riemann or something like that. But a Riemann sum is when we're looking at our function defined on our closed interval, and we have a partition. We're going to have delta x is the width of each of our subintervals, and for each of those subintervals, we're going to have x sub I star be any point in the interval. So we have an interval from x sub I minus 1 to x sub I, and x sub I star can be here, or it could be here, or it could be right there, or it could be here, or there. Anywhere on that subinterval can be x sub I star. A Riemann sum for the function f of x is defined as the sum from I equals 1 to n of f evaluated at x sub I star times delta x. Because we're looking at a regular partition, right? So we have this delta x that we're multiplying. It's the base of our rectangle. But the height of our rectangle is given by anything, any value that is within that subinterval. So looking up back at this, we could evaluate for a Riemann sum, we could evaluate at like the middle, right? So we could evaluate our function there. Sorry, this is very hard to see. So we could evaluate our function at the middle of our subinterval, right there, right there, right there. We could do something even more nonsensical. We could just like choose something. Like, I just feel like that point right now, but then I feel like this point now. And it's just gonna, like, any x sub I star in the subinterval is where you can evaluate your function for the Riemann sum. Riemann sum, so powerful. You're not limited to just an endpoint. Riemann sum. Don't say Riemann. That's not what we say. Riemann. Sound educated because you are. Riemann sum. Alright, so, if you have a function that is continuous and non-negative on the closed interval from a to b, and you have the Riemann sum, this is defined as the way that we said it before, for the function f of x, then the area under the curve, y equals f of x, on the closed interval from a to b, is given by a lovely limit definition. The limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star times delta x. We're just taking an infinite number of rectangles evaluated somewhere on our subinterval, and we're going to get not just an approximation for the area under our curve, but the actual number. The number a, which is the number found by this limit of the sum of all of our rectangles. So, the area under the curve is a number, just like a limit is a number, and a derivative is a number. We're looking at numbers. It's wild. Okay, so sorry, this video is getting kind of long, but there's just one more thing that we need to, just another vocabulary that we need to establish. So if you have a function, then you can find an upper sum and a lower sum. You can also find a right sum and a left sum and a midpoint sum. These are all different options. An upper sum is not tied to left or right, but is instead defined as looking at your local or your absolute maximum on the subinterval, and that's where you're evaluating. So it's looking at the extrema. A lower sum is again finding the area of rectangles, but you're evaluating your function at the absolute minimum or the global minimum on your subinterval. The right sum and the left sum, those are what we talked about before. The right sum is looking at the right endpoint and evaluating strictly there. The left sum is looking at your left endpoint of your subinterval and evaluating strictly there. And your midpoint sum is looking at the middle. So give this a shot. Look at the function f of x equals sine of x on the interval from 0 to pi, and find an upper sum, lower sum, right sum, left sum, and midpoint sum for n equals 6. And then I will put up my answer. Alright, so the upper sum is looking at your, on your subinterval, looking at the extrema, the greatest value, the global max on each of our intervals. So what I'm sketching in now is the upper sum, where we're looking at, on the subinterval, what is the greatest output, and that is where we're evaluating. So this very poorly drawn, sketched in, that's what we have. Those are the areas of the rectangles that we're aiming for our upper sum. So our partition size, that's, I think that's pi over something. Pi over 3? Pi over 3. Because we're looking at from 1 to pi. No, not pi over 3. Pi over 6. Pi over 6 because we're looking at our interval from pi to 0, and we're looking at n equals 6. So this is our b minus a all over n. That's our interval size when we're looking at a regular partition. And so we have that, and we're multiplying by our function evaluated at our endpoints. So we got, what, 0.5 plus 0.866 plus 1 plus 1 again, because both of these rectangles that I just colored in, those are both height of 1 plus 0.866 plus 0.5. So our upper sum, again, we're not tied to our left or our right endpoint. We're just looking for our extrema, or our absolute max on the interval. For our lower sum, probably change colors. So our lower sum is going to look at our same partition, but instead we're looking at the minimum, the global min on the interval. So from 0 to pi over 6, we have a rectangle of height 0. From 0.6 to pi over 6 to pi over 3, we have a height of 0.5. To 0 plus 0.5 plus 0.866, and that's going to be twice, right? And the symmetry is happening because our function is symmetric with respect to the interval that we're looking at. So 0.866 plus 0.866 plus 0.5 plus 0. Put a bracket there. For our left sum, we're looking at only the left endpoints. So that's very similar to our lower sum until we get past this vertex right there, or that maximum on our sine function. And after that, when our function is decreasing, our left sum suddenly changes. So our left sum is going to be pi over 6 times 0 plus 0.5 plus 0.866 plus 1 plus 0.866 plus 0.5. And that is our left sum. And our right sum is actually going to be like shockingly similar to that. So let me see. Is this going to work? Maybe. Whoa. This is like the those crayons, not those crayons, those colored pencils that were really cool when you're like 7. And like when you rotate it, it like changes colors. Do you remember those? So, I'm going to erase all these because all the colorful lines are getting very confusing. And we're going to look at the right sum. So we're looking at the right endpoint on our subinterval, and that's the rule that we're using. So here on this increasing part, we have a over approximation, but on our decreasing part, we have an under approximation. Wild. So what is that? 0.5 plus 0.866 plus 1 plus 0.866 plus 0.5 plus 0. And isn't that the same? That our left and our right are the same? So interesting. And what about our midpoint? So we could do a lot of work, and we could actually figure out what our function is at our midpoint. But I don't want to. So the average of our left and our right, they should... Does that work? No, that's right. Midpoint. We need to look at our function evaluated... Oh man, this is getting so long. We need to look at our function evaluated at 0.25, at 0.75, pi of 1.25, sine of, sorry, I can't speak words. I did that wrong. Midpoint. Back up. Midpoint is looking at our function evaluated at pi over 12. At pi over 6 plus pi over 12, which is 3 pi over, not 3 pi over 12. 3 pi over 12. Also known as pi over 4. And then our function evaluated at 5 pi over 12, sine of 7 pi over 12, sine of 9 pi over 12, and sine of 11 pi over 12. So that is where we need to evaluate our function. I really don't feel like doing that, so we're just going to write it out symbolically that it's our partition size is pi over 6, and we're evaluating at sine of pi over 12 plus sine of 3 pi over 12 plus sine of 5 pi over 12 plus sine of 7 pi over 12 plus sine of 9 pi over 12 plus sine of 11 pi over 12. And we should have 6 different, yes, 1, 2, 3, 4, 5, 6. And that should get us the heights of all of those rectangles that we're looking for the midpoint sum. So this is midpoint. Alright. That about does it. Sorry this is long. Have a great day.